you are all coming from different parts of the world, and welcome to VADSTI, Virtual Applied Data Science Training Institute. If today is your first time joining us, my name is Dr. Kwejan. I'm a professor at Howard University, and I'm the director of this program. So if this is your first time, the previous modules were recorded, and then you can review those, I believe, in the VADSTI GitHub. We are in module 5, and today's topic is neural network modules. That has been always a very interesting module, and many people want to know about artificial or neural network modules. But before I introduce the speaker for this module, a few housekeeping. For module 7, which is the tools for applied data science using cloud-based platforms, you will have to create a Terra account. I think the information has been sent to you. If you haven't received it, you can check on that in Slack. And then you have to create the Terra account. And then once you create the Terra account, there is a very short form that you need to fill. The form requires just your name, and then it also asks for your Terra account ID or Terra ID. So the Terra ID is just the email that you use to create the Terra account. It's not like numbers or letters or anything. It's just the login email that you use to create the Terra account. So that is what you use to complete that short form for the module 7 workshop. Also, don't forget to complete the survey, because always your feedback is very important to us to improve the things that we are doing. So today we are privileged to have Dr. Gloria Washington as the presenter for this module. Dr. Washington is a professor at Howard University Engineering and Computer Science Department. She's also the director of the Affirmetric Lab. Dr. Washington, I don't see her. Is she here? Gloria, are you here? Oh, okay, she is here. I didn't see her, so you have to make your face available. All right, so everyone, again, always I say when I'm doing the introduction, I want to see your faces, so turn on your cameras, and then let's welcome Gloria, Dr. Washington, for this morning's presentation. So Gloria, it's all yours.
Morning.
Gloria, okay.
Sorry. I'm used to, Zoom. Anyway, okay. So I'm Gloria Washington. I am so sorry I was a little bit late. I teach a Introduction to Human-Computer Interaction class that ended right at 11. So anyway, I just got out of that class. So thank you again for coming to this module today. Thank you for taking the time out of your busy schedules to actually want to learn more information about machine learning and specifically neural networks. So let me share my screen. Also as well, everything is uploaded on Codio, my slides, as well as the information that we're going to go through today in this part 1 presentation. Give me one quick second and I'll be able to share my screen. And just in case, I'll post the link in the chat for my slides as well. Just in case. Okay.
Dr. Gloria, I think you were kind enough to send us a heads up link. So the files have been uploaded to the course GitHub site. So if that would help speed up the process, the files have already been uploaded. The students have been informed. So if you check the chat, I've provided the link, and if you go to the Slack, the link is also there. So
yeah, sure. No worry.
Okay. Okay. So you should be able to see the presentation. If you can't, just go to the slides, which many of you have. So hello, everyone. Once again, my name is Gloria Washington. I'm Assistant Professor of Computer Science here at Howard University. My email, should you need to, is gloria.washington@howard.edu. So just a little bit of housekeeping. So some of the assumptions that I, as the instructor, take on when I'm teaching a class like this is that maybe you have taken at least one of the other data science modules that we have offered, and that you know some of the Python basics and you know a little bit about statistics and probability. The reason being is because some of the actual definitions and things, when I go through them, you're going to have to know a little bit more information about statistics or probability, mainly probability in general. Then also, I don't go over specific syntax or Python basics. I kind of assume that you've probably already taken that class. So, okay, so the agenda for this session is to find out, one, who I am, which will be very quick. We'll find out what is an algorithm, what is machine learning, and specifically, which you guys are here today for, is what are artificial neural networks. And some of the questions that are going to come up is, what is a neural network? A lot of you probably are familiar with the term deep learning. It's like a buzzword that everyone throws out there. I'm going to do deep learning anyway. And then what is back propagation and what is forward propagation? And one thing that is not mentioned on this slide is I do kind of tell you how neural networks fit into this overall AI scheme of when we think of AI and how machine learning fits in. Like, that's also a buzzword that a lot of people want to implement, but I don't think they truly understand like where it fits. Okay, so just to give you a little background about myself. Once again, Gloria Washington, assistant professor, received my bachelor's from Lincoln University and HBCU in Missouri. I'm from Missouri, went to George Washington in Washington, D.C. So my areas of expertise, the research that I perform at Howard, is more centered along emotional artificial intelligence, is also called affective computing, where we want to give computers the ability to interpret and respond or even sometimes mimic human emotion. So this area kind of fits with human-centered computing in general. And then since I teach a lot of computer science education courses like Python programming, C++, that's an area of mine. And then finally, since we utilize a lot of computer vision techniques, biometrics. So won't go into the awards or anything like that, but basically I do a lot of undergraduate research, and I'm really interested in myself and increasing the number of Black women who get PhDs in computer science. So I just ask that people mute themselves if you can. If you have any questions, let me know. Okay. Okay, so today, as I mentioned, we're going to find out, well, what is an algorithm? So when we think of an algorithm, it is a specific set of instructions that you as a programmer, and I'm assuming if everyone is in this class that you are a programmer, that you give these instructions to a computer to run or perform some sort of task. An algorithm is like a recipe. So I'm not a baker or anything like that. However, this was something that I Googled. So the recipe to bake cookies, it's specific steps that a person would actually utilize to bake a set of cookies. So an algorithm is like a recipe. And with that in mind, we think of machine learning is a concept that a computer program can learn and adapt to new data without human intervention. What this means is that we can give it examples of certain things that we have found that we want to predict something else in the future. A lot of times people like to say, if you think of it, it's like finding the best template or the best kind of overview of a specific problem, a template, or the specific problems related with a specific task, and finding the best template that is also suited for that task. More specifically, machine learning fits into deep learning. Deep learning within itself is simply a subset of templates we get to choose from that have proven effective across many tasks. So you'll see this in literature. You'll probably see articles about deep learning, but one of the things about deep learning is that it is composed of neural networks. And so it's these deep networks that have many different connections to each other. We'll go into what that means a little bit in the next slide. But basically, what we do in machine learning and deep learning in general is to use data to figure out the best numbers to fill a template, to fill this best template. And this is actually the learning part of machine learning. It's using input data about a specific task that you've given it to actually figure out what is the best template suited for that task. So what are the steps to machine learning? So as mentioned with an algorithm, machine learning also has steps, which is these are the specific recipe steps to actually perform machine learning. So when we think about it, we provide this input data. This input data allows us to specify what we think this template is going to look like. However, we can't even as a human visualize or even think of in our head all the different ways of how to visualize this output space of what this desired output should look like. However, we also try and, with our limited capabilities, specify the desired output. Usually the desired output is like a prediction, like a yes or no. Sometimes it can be a probability, it can be a confidence interval. But this desired output is to find the best parameters to transform this input data, this representative data that we have, into this desired output. And from there, we specify new data. We give it new data that it's never seen before to determine how well the neural network actually did. Okay, so what are some examples of machine learning? And I'm pretty sure you guys are familiar with some of these examples. From machine learning now has become so proliferated and ubiquitous that it's on your mobile phones. But when we think of an input, an image, a series of pixels from a photograph, and we output true or false on whether there's a car in the image or not. When you think of the CAPTCHAs or things like that, where you're going through and searching for a car in an image, in that particular instance, you are like the machine learning. And if you gave an image, if you gave the actual machine learning algorithm an actual image and tried to say, well, where's the car in this image? That is that true false output of whether there is a car is there. And then there also could be where you give it an image as well from a chest x-ray, and you want to predict the probability of the likelihood of the person having lung cancer. Machine learning is used extensively throughout health informatics research as well. And then another one is it's used in customer service, where you have an input of a sound recording of a customer service call, but then you have an output, which is a prediction on how the customer felt about the call with the score from 1 to 10. And input, and then finally, it's just translation tasks. So you've probably used Google Translate on your phone, or probably Google Translate even in the web browser to translate a particular word from French to English or English to French and back and forward. So those are examples of machine learning tasks. Before I go on, I know I'm going pretty quickly. Does anybody have any questions? Okay. All right, so what is deep learning? And the reason why I have to address deep learning is because neural networks in general fit within deep learning. But deep learning, as mentioned, it tries to mimic the structure of our brain. And the structure of the brain has many different neurons and connections between it. Deep learning uses this multi-layered structure of algorithms called neural networks. So it comprises of neural networks which could have more than 5 hidden layers. Usually when we refer to deep learning, if it doesn't have more than 5, it's probably just considered a truly regular artificial intelligent or artificial neural network, and that is definitely possible. However, a lot of people now in the research or in industry don't even refer to a traditional neural network anymore because of the advances in artificial neural networks that utilize deep learning. Okay, so when we think of artificial intelligence, where does deep learning fit? And artificial intelligence, basically, the way that I like to think of it, it allows us as humans to have this program that can help us do some things. It can help us sense, reason, act, and adapt. A lot of different, I guess, software that you may be familiar with is like recommender systems, computer vision systems. And then machine learning underneath this umbrella of artificial intelligence are the actual algorithms. These are the steps necessary whose performance improve as they're exposed to more data over time. So just saying that you're going to have artificial intelligence without actually including machine learning is not possible. And so even within deep learning, it is a subset of machine learning in which it's a multi-layered neural network. The neural network has to contain many hidden layers so that they're learning the output from each other. And we'll talk about how they're learning from each other with forward propagation and back propagation. Before I move on from this slide, I know that's a lot. Does anybody have any questions? No? Okay.
I did have a question, Dr. Washington. In terms of, you mentioned like 5 layers. Could you clarify what you meant by that? You mentioned 5 different layers to be deep learning or something. I couldn't quite catch that.
Yes. So when we look at the structure of, and that gets me, wonderful question, that gets me into the next slide. When we look at the structure of a neural network, what is it composed of? So a neural network basically is a short form of artificial neural network. And I included a picture the neurons that occur in the brain, and then also a picture of a neural network as to how we think of them, an artificial neural network. So the basis of neural networks are neurons, and within our brain, we actually have neurons as well that connect to each other and feed off of each other. So our brain is nothing but this deep network of neurons that connect and learn from the output and input from other neurons. And so we as machine learning researchers, we understand and we research how do we give this really complicated system new data, it learned from it, and then this network grows so that certain parts of it can get better at recognizing new and individual things as it relates to what this data is. So what is a neuron? Did that communicate it a little bit better?
It does. Thank you.
Okay. So a neuron within itself are these, the circles here. So when we think of it, a neuron actually receives input from other neurons. So when we think of in our neural network, the circles are represented here, and anything connected together is connected through a synapse. So usually within an artificial neural network that is used in deep learning, you'll have these things called hidden layers. And that goes back to the question. These things in the middle here are hidden layers, and they are used as understanding for the actual output. They transform whatever data that you've given it, whatever input data that you've given it, they transform it into a useful measure so that it can actually be used for prediction of the actual output, which is the output layer. So that's a really simplified definition, and we'll get into like some of the more difficult things. But when you think about it, we're just trying to mimic the way the human brain receives information, and computer scientists are doing really well because deep learning, for the most part, has really shot off. They're like, if you look at any research papers that come about, you're really not going to see research papers that only look at using a neural network that only has 3 hidden layers. Like, that's not going to happen. Okay. That out of the way. Okay. So how do we receive input from a neuron and then combine them together? So remember when I previously mentioned that we have some sort of input data that we encapsulate and we include it as a neuron. So in order to take that information from the neuron, we have to combine it together to actually be able to utilize it for a prediction or a classification. So we usually take some linear combination of inputs. So an example is, let's say we have X sub 1, X sub 2, and X sub 3. Now, in terms of things that you guys can think of, these are just examples of features. They could be actual numbers. They could be actual, data that you guys get from an image. They're just representative data that is input into your actual neural network. So when we think of it, we can say that we have some sort of function, some linear combination of the inputs, and this just allows us to transform these inputs into the outputs so that it is maximized. So in this example, where the actual blank is, and I tried to represent them with underscores, where the underscores are the individual blanks are these parameters that are to be optimized. And we want to optimize these parameters because it allows us to actually go to the output sooner. And the output, remember, once again, is either a prediction, a true false, a yes, no, a probability, whatever. And then actually weight, which is represented once again by the blanks in front of these actual inputs, are the weights that are assigned to each individual input data. Questions about this? In a nutshell, we take the input data and we use a mathematical notation to be able to transform it in some sort of linear combination of the inputs. So how do we figure out how to transform this input data? This input data can be anything, remember, and transform it to the output. So in order to do that, we must have an activation function. And we apply this activation function to our inputs. There are three types mainly that we utilize. One of the most ones that TensorFlow and some of the other ones have utilized is the Relu function. We'll talk about that. But the sigmoid function is basically a function which squeezes all this initial output and come from that linear combination between 0 and 1. If we think about a sigmoid function, you think about probability. Probability, you can represent it between 0 and 1 as well. And then there also is the tanh function. The tanh function is a function which squeezes all the initial output to be between -1 and 1. And then lastly, the Relu function, which a lot of researchers now start out with, is where it'll actually say if the initial output is negative, it'll convert that initial output to 0. If not, it'll just leave the output exactly like it is. Questions? Okay. So back to neural networks and the structure of them. So if the input of one layer of the neurons is the output of the previous layer, this is what actually gives us this deep learning structure. So for brevity purposes in this slide here, I just have this image where we only have 2 hidden layers. But if you think about most deep learning algorithms have several, sometimes they can have 1,000 hidden layers and they all propagate back to each other. But basically it's taking this input layer, doing a transformation of the actual data and transforming it so that it is representable for the output layer, which is, it can either be a true false, like I mentioned, a probability, a yes, no, or anything like that. Who has questions on this slide?
Hi, can you go over what a hidden layer is one more time, please?
Yes. So a hidden layer is actually a layer within a neural network that actually transforms the input data and it does an activation of it. So basically, it actually multiplies, depending on if it's a number, actually multiplies information together that is from the actual input and then transforms that so that it's representable for the output layer. Basically, it's a neuron that has this activation function that either has this sort of a sigmoid function, a tanh function, or a Relu function. It takes that input, does something with it, and is able to represent it as the output.
Okay, and in the second hidden layer, does it take the input from the first hidden layer?
Yes, it does.
Okay.
So that's how, let's move. Oh, well, I was going to give a quick example, but yes, what it does is it actually takes the output from the first hidden layer, and then it utilizes that as its input data. And so when we think about it, all of this information trickles from first the input data that you actually gave it to the first hidden layer, the second hidden layer, and so on and so forth. If it's a deep neural network, then it'll utilize the output of every individual hidden layer before it. And these activation functions are occurring in every individual hidden layer.
Can I ask a follow-up question? Oopsie. So when you say it transforms it so that the next layer can use it, what does that mean? Like, what do you mean by what defines whether or not the next layer can use it?
So the next layer will always be able to utilize it because the output of it will either be, depending on the function that you utilize, right? So if it's the sigmoid function, let's say you transform the input data that can be the pixel numbers in an image. You transform those to fit between 0 and 1. So whatever number that comes from that 0 and 1 is now the input of this second hidden layer here, right? So anything that is transformed here, the output of it then goes to this hidden layer here so that it's useful. Did that answer the question? Go ahead.
Yes, I understand that they're all connected, and that they're moving towards the output layer. But I guess how you get to those intermediate steps, that's just part of the algorithm working its way towards the output, to use very technical terms.
No, yes, basically yes. So we'll get more into an actual example, but you'll see, well, let's just get to the example. And then if I don't answer the question, you just let me know and scream at me. Okay. So let's say it again.
Oh, I'm sorry. I just wanted to ask another question because this is a fascinating and also confusing concept. So if every hidden layer is a potential input layer for another level, then theoretically that could be infinite, right? So how do we determine the terminal point to take our output data? How do we determine when to stop it? And right.
Yes, very good. That's a very, very, very good question. And hopefully you'll see a little of that today. So there's these things called epochs, and you could run your neural network for several epochs, right? And yes, it could go on forever, because if we think about this, like, you can let your algorithm run forever, or your specific neural network run forever. The problem with that is, and I don't address this until I think tomorrow. When you do that, you're only providing this input data. So it's learning everything that it possibly can about this input layer, which is this input data. The problem with that is it's called overfitting. And what you'll find is, because you've not given it new data, it'll learn everything about that input data, but you give it some new data, it's going to do horrible on. So that's the problem. But usually there are these things called epochs where you run it for certain iterations. And for most systems, I think like the one that we have set up that you guys are hopefully will get to today, it runs for 100 epochs. So it'll go through and propagate all of these outputs to the output layer 1 time, 2 time, 3 time, all the way 100 times. And it'll take the accuracy measures at that point and actually say, well, I've ran it enough, so this can actually be the accuracy of this problem that I'm trying to predict or classify.
Okay, one more point of clarification about that. So you're saying that if you run it too long, it'll become so specific that nothing fits that output. Nothing,
well,
it can't be generalized.
It's like, okay, I like to think of it in terms of my students, like undergraduates. Okay, so I'll give them a test, right? And or I'll say, I'll say, here's a practice test, right? And I teach, for the most part, I teach human computer interaction, but I teach programming. So I'll say, here's a practice test, guys, learn this practice test. But I'll also say this caveat: don't only look at this practice test. Everything that we specifically learned in the class that can help you program better before this test, go back for yourself and review it. What the problem is, these students will memorize and learn everything that's on that practice test. So the one time that they see a question that was not represented on this practice test, they'll get that question wrong, right? And that's actually what's happening with these neural networks, because they're learning everything they possibly can about this input data. But remember, you're trying to represent the problem as much as you can with examples from input data. But as a human, we can't even think to visualize or come up with different problems that it may encounter that are representatives. And that actually gets into artificial intelligence bias. Like when you think of facial recognition and you think of how these systems have been built on huge data sets that, you know, have millions of examples. However, the problem is homogeneity between the actual samples of the images. They're usually white and male. So what happens is they'll learn everything they can about those images. The only thing when you introduce like a person who has a little bit more melanin and something that they haven't seen before, it doesn't do as well. But that's a wonderful question. Any other questions? Let's see.
There's a question in the chat that asks if the activation functions can be mixed or used in tandem.
Yes, you're going to see an example of that. Also, one thing to note, I like to call it the secret sauce, I guess. There is no one correct way to learn, to have your neural network learn. Basically, it's trying to learn all the many different parameters that'll help this input data transform into the output layer, which is your output. So these parameters that is actually occurring within this activation function, they can be a mix of several different things. And you'll find that researchers will usually start out with a default, and we'll see examples of that. And the defaults are usually written within the actual code where you'll have an API or something, or even in Jupyter Labs, what we're going to use today. Where it's a default that automatically people will start out with, and then they'll play around with that information and figure out, well, my accuracy actually went down when I did this, or tweak these kind of parameters, but there's no correct way to actually achieve this optimal layer. It's just truly just playing with different things. And I'm sorry I can't see the chat. My entire screen are the slides, so I can see like you guys' faces, but I can't see the chat. So any other questions? Okay, so I'm gonna try and do hopefully a simple example that I hope will help a little bit more. Okay, so let's say, and remember that I like to think of in terms of being a professor or whatever, and sometimes these examples probably, maybe they'll communicate to you and help you a little bit more. But suppose we wish to predict whether someone will pass or fail their psychology class. Let's say that, and remember that the input data that you have is the input data that you have, right? So let's say I have input data from my class. Of course, I have the age, the sex, and the race. This is my input data. And then I have two neurons, which are in my hidden layer. And these two neurons represent homework and exam scores And these homework and exam scores will help me understand how do I transform this age, sex, and race into whether a person passes or fails. Now, this is a very simple example. It is not representative truly of all of the intricacies of what's going on. However, it is truly to get you to understand in a simple way of what could actually happen. Okay. So when we consider this example, let's say we have person A. Person A is a 20-year-old Black male, and the homework neuron, which is within, remember, that hidden layer, for him would output 0. And let's go through those steps just to see how. And when I was coming up with this example, I was coming up with this example of just Black is, I think I said 0 is for male and female is 1, right? So that helps me translate it to numbers, right? And white is 0 and 1 is Black. Okay. So let's say in this example, I decide to use the Relu function. And remember that the parameters, for the most part, the negative 200 is my bias. The 3 times the age, that is a parameter that I made up, right? However, what's going on with the neural network, these parameters, you can always tweak them, and they're not necessarily going to be 0.2 or 3 or 80. Usually it is those default numbers that that are already set up within the algorithm within like a Jupyter Labs or whatever. Anyway, so if we transform what I just said, where we take the person's age, which is 20, and if within this class, the way that I tried to think of the weights for the class is 20% of the class is male and 80% of the class is female. Now, this was just a heuristic that I used within this example to actually transform the output. But remember, once again, that these weights can sometimes be tweaked within the actual algorithm. And this is just a very simple example. Okay, so then I have 0.2 times 0 plus 80 times Black. And remember that Black is represented as 1. So all in all, I would get a negative number if you calculate it all together. Remember that Relu converts all negative outputs to 0 and all positive outputs. It just leaves it alone. Questions about that example? No one? Okay, sorry.
Why did you put 0.2 for male? This is 20% male, or just like you mentioned, Black 80%. That's a 0.80, or
yeah,
the pyramid.
Yeah. So, yes, sorry I didn't explain that. 20% of the class is male, then 80% of the class is female, and then 80% of the class is Black. Now, remember, I teach at HBCU, right? So 80% of the class is Black, and then 20% is other or whatever. So we'll just say white in this instance. So remember that in this instance, I decided not to use a decimal, which is totally fine. The weights do not have to be decimals, but for the most part, what you'll see when you're tweaking the parameters, they usually start out as decimals, and you can increment them by 0.1 or whatever, or increment them in smaller numbers. But basically, this was just an easier, simple example for me to kind of see how you can take this input and transform it into actual numbers.
And why do intercept is negative? The minus that was, so how do you make up the negative intercept?
So Relu, right, converts all negative outputs to 0. right?
No,
So
I
you
understand this one, but before it's minus 200, 200, this one.
say that again.
This one minus 200, how do you minus
Oh,
200?
that was just that's bias. Honestly, I couldn't think of a number, so I came up with that. Now, remember that related with the neural network, your biased information is usually given to you as well in the algorithm starting out with. And sometimes it is represented as a probability, but the negative 200 was a bias. I just thought it would be good to show an example where it is actually negative. I have to go get my charger really quickly, but 1 second. My computer has a low battery. I should have plugged it in. Sorry.
When you can, I have a follow-up question.
Just say it to me like right now.
Okay. Okay.
Yeah,
I'm not
I can hear
understanding.
you.
Okay. I'm not understanding the bias value. How you came, I know you made it up in this instance, but is that presumed error in the data, or what is that?
So, well, it is information that is usually relevant to your space, right? So the way that I like to think of bias is, well, I guess it could be, if you think about it, it could be almost thought of as like error. It's like, how likely should you actually listen to the input data? Is it a representative amount of data, or is it actually representative of the actual output that you need to predict or classify something? So yeah. Does that make sense?
At a very high level, yes. I think so.
Yes. So we'll get into a little bit more where you're actually able to see it. I am having problems. So I can't get back to the main WebEx. I lost it underneath all of these windows. And I have, can the TA, like, can you see?
Yeah, Gloria, we can see your screen. So how can I help you? Do you
So
want?
it is, oh, there it is. I see it. I'm sorry. 1 second. Okay, it was, I am sorry about that. It was, I have 1,000 windows open. Anyway, okay, so you're seeing my screen. Okay, so in this example, remember that this is a really simple example to show you how this input data could be transformed into actual numbers so that you can utilize them for the actual output. Okay, so in this continued example, let's say I have a 42-year-old Black female who's also in the class, and I have the exams neuron. For this female, that's a typo. Yeah, forget this second part. That's a typo. So let's go actually into that actual example. So we have, once again, this bias. And let's say for exams, we have 6 as the parameter that's used in front of the actual age. And then we add that together with 0.8 times female plus 80 times Black. So we transform that, and remember that Relu leaves these non-negative outputs to be, they leave them alone. It doesn't mess with them at all. So in this example, if my math was correct, it was 132. Questions? No questions? Okay. Anyway, all right. So continuing along in this, go ahead.
I had a question for the example again. Can you go back over that again? I understand about the Relu leaving it non-negative, but as far as the information that you're given, you said it's biased, and normally you would be given information that you would put in. Is that correct? Like the negative 200.
The negative 200 usually within your package of like that is connected with the software. So, like, there are people who already build artificial neural network software to utilize. So the one that we're going to utilize today, the bias that's put in is usually a default number. For the most part, it's usually put in as like a decimal point, or it doesn't start out at this huge number that I gave it. This example here is truly for purposes of, just to show you an example of how to take this input of these numbers, this data, and transform it actually into output that is utilizable by this artificial neural network.
Okay, and you were saying the number 6.
The 6? In this example, the 6 is, it was just also a weight that was multiplied by age. It is a number that I came up with for this example. So exams is different than going back.
Homework.
Yeah, it's because there are 2 different hidden layers, right? Or 2 different examples of neurons that are actually hidden within this hidden layer. So it's just a different example. Okay.
All right then. Thank you.
Yeah. And you'll actually see real numbers that come out of the actual output rather than this example. If that information, interests you. Other questions?
A question: why you said hidden layer? Because you are giving active intervention, like an exam, who are taking exam or not, right? This is not a hidden layer because you are giving active thing, like okay, if I take the practice test, I'll pass. So it gets some information, but you mentioned it as a hidden.
So in this example, remember that the neurons that are within the hidden layer are utilized to transform the input data into output that the output data can actually utilize to say whether it's a classification, a prediction. In this case, it is predicting pass or fail. So it is in the hidden layer. This is a simplified example to show you guys how a hidden layer is utilized to take output from this input layer and transform so that it's utilizable by the output. This isn't something that you would actually see, right? So homework and exams are neurons within the hidden layer. it goes back to the definition of the hidden layer once again. So remember that the hidden layer is composed of neurons that actually are able to, that has an activation function, and it is a linear combination of things and parameters that actually allow you to take the data that's given in the input and actually use it for the output.
So the example you gave earlier on, you mentioned that the output of a hidden layer can be an input of the next hidden layer, right?
Mm-hmm.
So this example, I don't see that happening because the
You
homework,
won't.
yes, so it's
In this
different.
example, this is not, it doesn't show more than one layer. It only has one. So if there's two neurons that are actually represented in the hidden layer in this example, you're not going to see anything else because I didn't come up with more than one hidden layer. This was truly a simple example to show you how to take input data and transform it and utilize that output for the actual prediction or classification. In this case, pass or fail.
Okay.
Yeah, Dr. Gloria, this is William. In fact, that relates to the question I posted on to you. So then that connectedness actually happens if you have more than one hidden layer, because in this case here, I would have expected your performance in your homework to reflect or to be reflective in your exams grade. The more practice you go through the homework, the most likely you're going to see some of these homework principles being shown in the exam. But we don't see that now because you don't have more than one hidden layer. That's probably what you're trying to say, right?
Is that also what you just said is the number of times that you practice. That's input data, right? If you are given an average, let's say this is average homework scores of even the entire semester, what you just said was input that can be utilized by the neural network. So if you're only given these scores, which allow you to transform this input data to be useful, then you can only utilize what you're given. Other questions?
I'd like to see more examples, so we can go on.
You'll see more examples. This is a simple example. So remember that, do not think of this as something that you would actually see. This is taking actual input example and being able to transform it into useful output. You wouldn't see this in a normal artificial neural network. Like, not this, not these numbers, not the way that it's represented. Okay. Okay, so the output in this example is 132. So remember that Relu leaves non-negative outputs alone. So if we go along with this example and we calculate the exam score for person A, which would be 0 because it would be negative, and then person B's homework score is 6.8. These scores contribute to the final output of passing, right? So remember that passing is yes, no. Should a person pass or fail, right? T, true or false? Okay. It is the probability of someone passing based on the output of the two intermediate neurons. The two intermediate neurons in this instance were homework and they were exams. So the two intermediate neurons were homework and they were exams. They are represented as a hidden layer because they actually include an activation function, which allows us, when I say us, the programmers, to take this input data, transform it into useful information so that the output can utilize it for a prediction or a classification. In this case, it is whether a person has passed or failed. Okay, so in order to get the probability of all of that together, we then take, in this simplified example, we have a pass parameter that we calculate where we say, remember, sigmoid actually allows us to fit numbers between 0 and 1. So we have a sigmoid function where it's -3 plus 0.10 times homework plus 0.25 times exams. Let me explain. -3 is a bias, right? 0.10 in this example was just the weight that I pulled out from what I would say 10% grade goes to your homeworks or whatever. Remember that that number that is usually in front of these neurons is a weight, right? So exams, I say, well, that's, 0.25. Questions about this?
Yeah, come in.
Yes.
Come in. Come in, please.
Hello.
Yes.
How are you?
Been a while. I will see you this year.
Could you mute yourself?
Please mute.
Okay. So questions about this example. None? Okay.
Is this it looks like a logistic regression function, right? So yes, like outcome, yes, no, based on these things. So it's kind of a statistics, logistic regression function.
Yeah, so basically, logistic regression does mimic neural networks, however, does have a lot of statistics that are involved in it as well. However, remember that the activation function, depending on how it is utilized, doesn't necessarily translate as evenly to statistics. So in coming into this is truly the output that you're concerned about, right? So like the pass function in this example would actually give us a probability. So your output that you can say in your examples are, there's an accuracy measure, which usually is outputting you'll see an example of today. You can make it be a probability, you can, or a confidence interval, depending on how you utilize the actual output, but this is a simplified version. And the reason why it does mimic statistics in this example, I wanted to make it as simple as possible. Other questions? Okay. All right, so to actually get the person A's probability, plugging in all the numbers, I would get a sigmoid of -3. And that would translate to 4.74%, right? And then person B's probability would translate, I would get a sigmoid of 30.68. And that sigmoid would translate to 99%, right? So there's some issues with this, as we can see, right? And what are the issues? What does this tell us? Before I move on though, questions about this slide?
Negative minus sigmoid -3 convert to probability 4%. But here sigmoid function positive, but still 90%, 99%. It's a negative versus positive. So how do you convert minus negative to this percent?
Great question. So there's this Sigmoid calculator. Basically, I'll put the link in the chat. 1 second. I use the online calculator. That's the simple answer to it. But basically, there's a sigmoid function calculator that basically converts it for you, but it's 4.74. Trying to find the link in my mini windows. I'll have to post it in the once we actually move along to an actual real example. It's going to take me too much time to find it, but there is a Sigmoid function online calculator. If you do like a Yahoo search, Google search, whatever, it comes up usually as the first one. Questions? Okay. I'm waiting a little bit because, I just want to be sure. Okay. Anyway, so what does this tell us? Basically, it tells us that neural networks are interesting, right? Age, race, and gender, or age, race, whatever combination of things may or may not be a good indicator of passing a psych class. There's a lot of information that is missing, right? So neurons and neural networks are not that simple. That should say are not that simple. In neural nets, the best intermediate features are figured out to lead to an accurate prediction. The hard part of actually thinking of it as a human, being able to take this simple example that we have, it doesn't ever work like that, right? The reason being is because usually how the output is propagated to each individual neuron and to each individual hidden layer is more complicated than this example, than this simple example. And the reason being is because of the activation functions that are actually going on. And these activation functions, everything trickles to each other. So this simple example is not indicative of what you would see normally within a neural network. It was an illustrative example to show you in the simplest way possible of how a neural network translates this input data, transforms it into numbers, and how this information is used to say whether a person has passed or failed a psych class. In this case, we saw that the person who was 20 years old had a probability of 4.74% of actually passing the class. But there's so much other information. As mentioned by the TA, it could be number of study hours, number of times you went to the tutor, cultural information, your home life, especially now with COVID, where do you have a dedicated or do you have a dedicated desk? There are students who are doing their homework in crowded apartments. There's a question? No? Okay.
I do have a question. And I think it follows on that person who asked about a second layer, right? So there was no second layer in that very simple example, but what you're talking about may be then the second layer. So my question has to do with, are the layers then, they're differently weighted. So if this is in fact a regression equation, then the most heavily weighted, are we assuming, are the exams and the homework, and then all those other variables that we've not yet accounted for would be differently weighted? Do each of those levels indicate a different weight? So in that would also be like class attendance, right? And all those other variables that you're talking about. Is that what identifies the second layer or third layer or fourth layer?
So I want to caution you, a lot of people recognize the similarities with regression. However, the way that the weights are communicated and the way that the output is communicated to other layers is different. So in this example, what I was truly trying to show was a simple neural network, not a deep learning neural network. And then to go back to your question, the reason why I caution you against thinking that the weights would always be the same for each individual neuron, that's not necessarily the case in deep learning artificial neural networks. The reason being is it's not as simple as the way that I represented it. So each neuron has an activation function that it's different for each individual neuron, right? So in this example, I represented exams, I represented homeworks. Those were within the same hidden layer, right? And there was only one. However, when you go along to actually having more than one, the output that comes from each individual neuron is totally different. And the weight may be different because the activation function of how it actually utilizes it is different. So I want to caution you from you know, there are similarities with linear regression, which, you know, I definitely, linear regression in general, I definitely can see. But with deep learning, the way that the actual numbers are propagated to each individual layer is a little bit more complicated than that. Questions? And I will say, as I'm not a statistics person, right? And I don't know, we didn't do an introduction. However, if a lot of your background in the actual audience is probability and statistics, actually understanding neural networks and what's happening for a lot of, at least for me in my experience, statistics, persons with that background, it kind of angers you. So yeah. Is there a question? I can't see the chat, so is there a question in the chat? No,
No,
if not,
actually, no. I just posted the output of the computation that you did for one of the users.
thank you. Okay, so one of the things to remember specifically about machine learning is it can only learn from the input that you give it, right? So in this example, age, race, and gender are probably not good indicators of passing a psychology class. You need to give it more information as mentioned. So this simple example was just to show you how to take these numbers, do a transformation on them to be able to come up with a probability that tells us whether a person would pass or fail. It was not an example of a deep neural network. It only had one hidden layer and two neurons within that hidden layer, which were homework and exams. Okay. So as mentioned, number of hours spent studying, average hours spent studying, all of that more contextual information may lead to more accurate predictions, and that's why the input data is very important. Okay, so as mentioned previously, remember that there was 2 steps in machine learning, right? That simple example was just a simple example. We're moving right along to how do we learn from the data that was actually given to us? So how do we find these optimal best numbers that fit in our template, and how do we perform this optimization? In order to do that, as the programmers behind the scenes, we must say to ourselves, well, what does best mean in regards to the problem? And when you have that best and you defined it narrowly, you should be able to then come up with a metric to tell you how well the model performs. And we want this prediction to be as close as possible to the actual value that of what you define best to be. So important cases of prediction, when we think about like cancer prediction, we think of, I don't know, they have prediction, machine learning and deep learning algorithms that can predict elections or whatever. Those are like when we think of those specific cases, you may want to penalize the model for improving the actual performance and the accuracy of the model that actually comes out. And I wanted to throw a buzzword, which is something that we have started to in computer science or even just in general. It's called reinforcement learning, where you give examples to the actual deep learning network, and then depending on the prediction of whether it was right or not and how close it was to the actual metric that you defined, you would penalize it for any predictions that it got bad or was bad, and you would have to define whatever bad would be, right? So in the case of bias in machine learning or in facial recognition, we always go there. At least I always go there as a biometrics person, right? So if I've given it a case of 100 individuals and it performs horribly on 10% of the Black individuals that were actually went into a system to try and have access to their data on their computer, and they use their face recognition. Like, I could penalize the algorithm in cases where it got a prediction wrong and it didn't let that person actually into their system. There also is this rewarding as well, where you can reward it. I've seen for the most cases people penalizing the model more than I've seen rewarding it. Okay, so a metric for neural networks that is used everywhere. So this is something that you will see forever. Well, when I say forever as long as you're in this class or in learning about neural networks in general, is the loss function. The loss function actually says how badly this model that you created by having this input data or whatever, how badly the model is performing based on how far off the predictions are from these actual values in the data set. And we want to minimize this loss function to put it in as simplest terms as possible.
What did you know? No. That's my brother.
Can you mute?
Oh, okay. Okay.
Can someone mute him?
Saturday night, because tomorrow they do come. But today, if I call you myself.
Can the TA mute him? I can't see him.
Yes, one moment, please. I'm trying, please.
The one they use for it.
Unfortunately, we don't have that permission. We don't have that rights to. I think Stacy does.
This person doesn't have the mute button next to the name. I can't mute them for whatever reason.
Okay. Anyway, and to put it in as simplest terms as possible, right? It is the probability of the model that it has predicted a correct label. And it takes a negative log of that. That is the loss. So a common loss function is the softmax. The softmax.
It's better say you go back to 1213. Because now I have to.
Can somebody text him since he is like
strong for them. But they want that old
Lord. Okay, so what is the softmax loss function? So the softmax loss function is the probability that the model has assigned to what we know to actually be the correct label. In the simplest terms as possible, right? It is the probability that our model has predicted the correct label. Okay, so simple example. So say I want to train a model to predict whether an image is a dog or not. So I've trained this model. It's given me output of 0.78, right? So think of the simple model that I came up with, right? So the probability of person A was 4.74. The probability of person B was like 99%, right? In this example, if I had trained the model to learn from a dog, it gives me 0.78. That tells me it's saying that 78% of the time, we believe that the examples that you've given us have been examples of dogs. So the probability that it's not a dog is 0.22. So to compute the loss function in this example, we would take the 0.78 and do a negative log on that. Our loss function in the simplest terms for this particular simple example is 0.1079. Questions? Okay. So another example is, let's say we train another model that actually gives us the probability of dog to be 0.35, but we say the probability of not being a dog to be equal to 0.65. In this case, our loss function of the probability of dog, if we just take the negative log of that, will be 0.4559. So in cases of neural networks, we want to minimize the loss. The reason why we want to minimize the loss is it helps us create the best model possible for our input data. I'll repeat that. The loss function helps us as programmers, people who are machine learning researchers, whatever, anybody, a consumer of machine learning, it helps us to minimize the loss of our models. And we want to minimize that because it helps us create the best model. Okay, so the idea in this loss function, the softmax function, if you look into it's called the gradient descent, I'll just say that. The idea behind gradient descent is to move the parameters slowly in the direction to where the loss will decrease. So you're probably asking, well, what's the parameter? I forgot what that is. Remember, the parameters are the weights, the biases, it's everything that goes into that neural network that allows us to transform this input data into an actual representation so that the output can be either a prediction, a classification, a probability, whatever. So we want to make sure that that loss is decreased in the smallest. So what is gradient descent? Okay, so gradient descent actually allows us to find this minimal amount of loss. And we then will be able to utilize this minimal amount of loss in our neural networks. So in this example, it's saying we have the new parameters and it's equal to your old parameters minus the step size times the gradient. So in this example, remember you want to make sure that your loss is minimal. So you want to find this global minimum amount of loss, and your weights is represented on the x-axis here. So a lot of times in machine learning, you'll start out where you take elephant steps, right? You'll tweak parameters that actually occur within the software, and you'll take a big step. And you're like, oh, okay, well, gosh, my accuracy improved. So let me do one more big step. But then you find, oh, wait, no, now that I did that, my accuracy is messed up and I got 0.2. Whatever that means, right? But so in that instance, you then want to move along to baby steps, right? And these baby steps usually relate to, depending on the software, right? Some people will modify it by like a 0.1 or a 0.2 or all of these smaller increments so that it is moved along until we find this lowest point within this curve. And this lowest point is the winning number that you utilize in your neural network. Before I move along to that, questions about gradient descent. Okay, so that leads us to backpropagation, right? Remember that gradient descent has everything to do with the parameters, tweaking the parameters so that you can minimize the loss and minimize and create the best accurate prediction as possible based on the input that you've given it. So what is backpropagation? And we had talked about that a little bit previously, where I mentioned that the output from hidden layers propagate to other hidden layers actually within the neural network. Backpropagation is a way to find the gradients in a neural network, right? So this goes back to why that simple example, I maybe shouldn't have showed it to you, because you're thinking that it's that simple. However, it's not, right? Because everything propagates to each other in a neural network, and the neurons that you have within the neural network all propagate in different ways. Sorry. The gradient in an earlier layer can be expressed as a simpler function of the gradient in the layer after it. So in order, just from the name alone, it just says what you're doing is starting from the lowest or the last layer actually within your neural network. You find all of the gradients for that, for all of the neurons within that hidden layer. And then you work backwards. And I'll say this is like, you're not doing this by hand kind of thing. So the software that you utilize is going to find all of those gradients, the lowest amounts for each individual hidden layer. It's finding all of those automatically, and you're starting from the final layer and then working backwards. Questions? Okay, so a lot of
I'm
that,
sorry.
yes.
I'm a bit delayed in getting on. I'm sorry. Just a very simple question. Why do we want to do that?
Loss, yes. So remember that each individual network, right? We want to minimize the loss, and minimizing the loss allows us to actually compute or actually have the best prediction possible based on the input that you've given it. And so that goes back to this, right? Gradient descent, it helps us find the parameters. Remember those parameters, these are the W's that are in front of all of our input weights, right? Remember, I would have to go all the way back, but those blank spaces actually within our network, that is a linear combination of all the input data, that weight allows us to find the minimal number of loss for each individual network, each individual hidden layer network within our entire deep learning neural network. Basically, it helps you find the weights. It helps you find the minimal amount of loss that you would have, which would be a better prediction. Other questions?
So just to clarify, for those weights that you start with, it's going to correct your weights or adjust your weights. So you don't really have to have any really informed weights. I guess maybe you can make good guesses at it, but it'll sort of iterate till it finds a better weight.
Yes.
Is that correct? Okay.
And that propagates throughout the entire network. So like I said, deep learning sometimes can have thousands of hidden layers. So like with backpropagation, it'll start at that last layer, figure out the lowest amount of loss for that entire layer and those individual neurons, propagate it. So it'll propagate it all the way back to the first hidden layer so that it actually comes up with the minimal amount of loss for your entire neural network.
Thank you.
I will say most algorithms now are, you can specify based in the when you're setting up the actual code or whatever, where you want it to be back propagation or forward propagation. But most people, for the most part, start out with back propagation because it allows you to work a little bit better. Okay. Okay. So, but before I go on to that, I just want to make sure that I'll go back to this and that I've answered any questions as it relates to why this is important. None? Okay. In summary, that doesn't mean that we're done. It just means that we are done learning the background. Anyway, so in summary, machine learning, remember, has 2 steps for the most part, right? Where we specify a template, we find the best parameters for that template. The third implied step, as to what I said previously, is how you determine how well your model even, how well it is, even on a task that you give it, is where you give it new data and then see how well that template is at prediction or classification or whatever you're trying to do in that particular example. So a neural network is a sophisticated template, right? Deep learning, for the most part, has all of these many hidden layers that feed into this model. They have complicated relationships between the input data, where the input data is transformed into actual numbers so that the output layer, we can actually utilize that information to say whether something, in this example, whether a person has passed the class or they should, or predicting that they passed the class or predicting that they failed, predicting that an image is a cat, predicting, that a person is who they say they are from a biometric standpoint. But basically, machine learning, and the reason why it's so important that we're having this class, is neural networks and deep learning neural networks are utilized in almost every aspect of healthcare and in society. They're so ubiquitous that now our cell phones are able to utilize them as well. Okay.
Regarding the forward propagation, because I know you talked about the back, but you didn't get towards the forward.
Yes.
Propagation.
Forward propagation is just the opposite, right? So it finds the gradients, it starts at the beginning, and then it minimizes the loss for each individual hidden layer within it, and it propagates that output to the next layer and the next layer and the next layer and the next layer. So it's truly just the opposite of back propagation.
Thank you.
Mm-hmm. Okay, so in this next step, stop sharing. In this next step of what I wanted to do was to allow you to practice. And the examples that we had. So I'm trying to find the folder name. 1 second. Okay, so the folder that you guys can practice under is there. So I gave several different ones. I would probably say the one that will be most beneficial and useful to start out with is the folder that says deep learning tutorial, right? So let me share my screen so you can see what I'm doing. Okay, so underneath this example, this is a really simple problem. Not this, this is the README, but if you want to look at that, you can. Anyway, but I have uploaded a Jupyter notebook and then also a comma separated file of house price data. I think it logged me out. Okay, while that is actually loading.
I think it's a coding companion.
Yeah. Okay, sorry. I need to delete the untitled one. Anyway, so this is a very simple example. It also takes you to a website where you can learn more information. I also need to mention that those slides were based on this website as well, which has a book as well, which I thought was like one of the most simplest ways that it explained artificial neural networks. And from the perspective of being a professor, it just puts it in the simplest terms, I'll say that. Anyway, so in this example, you're going to look at creating a neural network. You're going to load data from that comma separated file. Everything should be there. You should already, I believe, in some of the other modules, if you have taken them, learn how to start up your Jupyter notebook. But basically, you go through. And one of the key things is mentioned that you have to do within this actual Jupyter notebook is I had to install pandas. You actually are using a package called sklearn. Basically, sklearn and Keras are pre-done software that some wonderful person out there has already put together an artificial neural network, a deep learning artificial neural network for you. So we actually import those, and if they're not already pre-installed, you have to actually run this part for the others to actually work. So what I wanted to do was give you time to work on that and then virtually walk around and answer any questions that will possibly come up of what's going on with the software. But what I'll do really quickly is just to give you an overview of the steps. You're installing the software, you're exploring the actual data and loading it into the actual Jupyter notebook. You're going along from there and creating a neural network. And you're creating these weights and stuff like that, right? So X scale and Y scale are actually weights that initially is starting out with. These weights in general, you can tweak, and it's just all has to do with this sklearn package. To look more into the sklearn package as well, if you go to the website that I previously provided, also they have an API documentation, but it just tells you behind the scenes what's going on. You're training the model, you're building your first neural network, and just to give you an overview, this is a deep learning neural network. It has 30 neurons. It uses the Relu function, and it has these 30 hidden layers. So the simple example I gave you was not something that you have in this example. So I wanted to give you time to work on that individually, and we help you as needed by answering any questions. Any questions that comes up from this?
I had a quick question about sort of just like the data layout. Should we use it sort of like, let's say we have multiple measurements for a student in a class. Should we have it like in long form or wide form, or does it, how does that, what's the best way to?
For the comma separated file, you mean?
Right. Mhm.
So that's a really good question. It's whatever you have, and if you're able to, one thing to mention, right, in the simple example that I gave you, black, white, male, female, right? So being able, a way to transform those into numbers, because there are software where it can utilize and map those categories for you, all the rest of that, right? However, you know, if there's an easier way that you can represent it, like this person was a male by 0, a 1 actually being a female, it just makes it a little bit easier, you know? But we could take a look at this too. Of course it doesn't. Anyway, it's down. This is the way that it's represented from this housing price data. And you'll just see like it doesn't have any categorical information, but the stuff at the top, it just tells you all of the information that's included in that one file. I would say throw as much information, you know, as you can. If you have about, you know, your students, and just any categorical information, if you can represent it in a way that it could be a number.
Thank you.
Other questions? Let me know if I didn't have any problems installing these packages last night, so, but let me know if you do. Also, one thing to mention as well, I was getting not a runtime error, because I don't want you to get concerned. I was getting a timeout error, and it has to do with the number of epochs of our deep neural network, right? So I mentioned epochs before, right? So it's basically, it's running this neural network, and each time it outputs something, it outputs the accuracy of that accuracy at that particular moment, the steps, the loss. There also is value loss and value accuracy. This information is just information that it utilizes to inform the other, to actually inform the other layers of the neural network. But in this example, it ran all the way for me a second time. So if you get that it's timed out, just let us know.
Dr. Gloria, a quick question before we start. So for our internal setup in Codio, I think you have to do the install with a sudo in front of it. I posted that in the chat. So if you try to, yes, so that in our setup, you are a user, so you have to use a sudo. In your setup, you were the admin, so you didn't have to use that. So just for the class sake, for as we did in previous classes, the exclamation, the bang, has to be a sudo pip3. So a sudo space pip3. If you look in the chat, I posted that. So that's the only problem you have.
And also another thing to mention that goes along with that as well, like once this class is over, don't feel like you can't take this, you can export it, right? So there's Google Collab. For the most part, many of my students utilize Google Collab. Google Collab and Jupyter Notebooks flow between each other very easily. The only difference with Google Collab, like I don't even have to do the pip3 install of any of my libraries. It just will automatically know if I'm importing a library, it will automatically install it for me. So don't feel like you can't take this notebook to something else and practice on your own, you'll get a little bit more familiar with what you need to install, because you'll get these really weird errors. But for purposes of this example, you should be good to run each of the cells without having an issue. And then you'll be able to look at some of the output and some of the accuracy measures that are coming up from this example.
So, Dr. Gloria, do you have an estimated time for students to try this on? 10 minutes, 15 minutes?
Oh no. It took me 30 minutes. So it'll probably take you, the rest of the class, take your time. If you run every cell without understanding it, yeah, you could probably get done. But if you truly like, some of the questions that we got previously were like really wonderful. So if you want to see like what the output is doing, what's going on, how the model is fit, how you see how you can just play around with different parameters in general. Like some of those questions were really good. And if you want to try them on your own, by even modifying whatever you have here, you can. But definitely don't just press the run button, try and understand what's going on. I also want to mention as well, and I showed it in my beginning slide, my email, gloria.washington@howard.edu, if you would like to, converse a little bit more. Of course, you're going to see me tomorrow, but converse a little bit more. And if you have any other questions.
I have a question just as we're looking at this data running. You're at Epoch 92 out of 100, 93 out of 100. There was a point earlier where the accuracy, 0.89, 0.89, pretty good accuracy, pretty high accuracy. So is it fair to assume that as your epochs run, your accuracy will get higher, better?
In some cases.
Okay.
However, there are times where I've run for 100 epochs and it's got progressively worse. I will say this is more of a simple, like housing price data. Like it is a simpler example. When you get into more sophisticated things, there are times where the accuracy gets worse. I'll just give you guys an example. I have a student in my class who's doing natural language processing, and they want to learn how to use natural language processing of like what's already out there. So let's say you have a Google Translate and you have the output from it, and you want to determine if a person is code switching within that output. So those are two different things that inform each other. But in that example, our accuracy got lower as it learned. And it could be a myriad of things. It could be our parameters, but it could also truly be that we have not provided enough examples for it to learn from of when code switching is occurring in text that has been translated, and many different examples when they're going back and forth and back. So that's an example. But in this case, it is great that it is getting better. Like in Epoch 87, it went down though, you see. But one thing to note as well, in that example where it went down, the loss was 0.2592, and the loss in the previous epoch was like 0.2890. So that is an example of why that loss function is important.
Dr. Washington, I noticed in one of the models, it was used Relu and Sigmoid together in one of the models. I don't know why we use them together. Is that because you want to compare the outcome between the two?
Yeah, so remember that there's no fixed way to do it. You can utilize Relu, you can utilize the Sigmoid, you can utilize 10H. It is specifically related to like your problem. In the case of the simple example I gave you, we use the Sigmoid function to fit everything between 0 and 1. So probably what's happening in this example is, since it's using probability, it's probably using a sigmoid to fit everything between 0 and 1, but it's using the Relu to actually output 0 if it's negative and just leave it alone if it's positive.
Yeah.
So that's probably is combining those two together. But you can utilize different combinations together.
Okay. Thank you.
Dr. Gloria, I have a quick question. I know this is a hypothetical example, but in your in the use of optimizers, the first one you use the Adams optimizer. Oh no, you use a SGD optimizer, and then the second model, which is model 2, you use the Adams optimizer. So in this case, then you're going to compare apples and oranges, or would that not have any effect besides the number of hidden layers being more in the second one? Won't the optimizer also cause a difference in basically, won't that also give one an advantage over the other?
You're down by adding regularization to our neural network, like here, binary. So the first one does atom optimizer, and then you said the second one does
and then the top one, the one with the model, did only the I think it did the FDG optimizer. So if you scroll up a little bit, the first, your first model.
Okay.
Yeah.
Yes. So it's not really in this example. This example truly is, it's okay to use two different optimizers to find the lowest global minimum, right? So the gradient descent, remember, is what you're trying to optimize and find that lowest number. And you want to compare which model is better, right? So that's why you want to change them in this instance to say, okay, well, model 1, maybe it wasn't as good. And model 2, it gave me a little bit advantage over the other one, because the number that's most important, depending, well, to you and to me actually as well, is this number, 0.89 blah 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 blah, right? So in biometrics terms, I want that number to be as close as like people are having accuracies as close as 99.19% or 99.9%. So whatever number in whatever model that gives me the highest accuracy is what I want. Regardless if one uses an optimizer, that's different. Yeah.
And then also, I know the number of epochs is costly, especially if you are using a cloud environment or if you don't have time to wait. So your idea also is to catch the point at which you have a plateau. So let's say in the first model, you were flattening at epoch, let's say 20. So then once you determine that, then in the testing stage, you don't want to go beyond 20, right? Is that the idea is that the idea behind this accuracy versus epoch plot?
No. So 20, like it, well, okay, I shouldn't shake my head. No, it depends on you, right? In terms of biometric tasks or like the tasks that we perform with some of my students, you want to run it for definitely more than 20. Some people will sometimes have their models running for days, right? And this example, of course, just shows you like an epoch of 100 to start out with, but you do want to run it so that you get the best score possible when in terms of accuracy. Because if you don't run it long enough, it doesn't learn your input data long enough. And anytime you give it new data, which is data that is never seen before, it may perform horribly. So when I say horribly, like 40%, 60%, in terms of biometrics, you couldn't say to a government agency is not going to buy software that performs at 60% accuracy because of the importance of the task that they do. Like they're not gonna, yeah. So I'm gonna get me some water and I'll be right back. But remember, you truly are just modifying. If you want to continue to play with this model, go through and try and understand what it's doing. Remember that this is an example that utilizes software from sklearn and then also from Keras, which is just a package. Okay, I'm back. I wanted to just give everybody time to work on this. So if the others, I know that they're going to work on this a little bit later. I know we still have a little bit left in the class, but if any other questions come up, of course, I'll be around until the actual end of the class. But you're just working on this, and I'm answering any questions, and the TA as well.
So if I understand this correctly, we're supposed to go over the code and trying to figure it out, right?
Yes, see what it's doing. As mentioned, it uses a neural network that people commonly utilize and set up, so you know how to set up one on your own if you have problems on your own that you want to actually utilize a neural network for.
Okay. I have some questions about the some of the code.
Yes.
Could you explain lines 12, 13? Lines 12 and 13.
Okay. 1 second. Can you just tell me the section? Sometimes your line number is off because when you run it, like what section is it under? Is it exploring processing?
It's under. It's just exploring and processing the data. It's just the training and setting apart the training and the testing data, the training and testing sets.
Yes. So yes. Okay. So one thing to mention as well. So remember the input data, or actually remember the example, the very simple example where we had age, race, and then gender or sex. So that is actually input data. Input data can be divided up to a training and test set, right? So a training set is what you will utilize to train your model. It says that, well, these are all the examples of this particular problem, and this is the data that represents this particular problem. The training set is actually utilized to create this template, this best template of what this actual optimal output would look like. Then from there, you have a test set. The test set is usually a subset of that input data. So what the model does, it doesn't learn from that test set. The test set is actually utilized to say how well the model is at predicting when it hasn't seen some data before, right? So you may have examples that are in both, right? That example. So when I say examples, I mean like you may have age, race, and gender in each of them. However, in the test set, it just hasn't seen them before. So it just tells you how well your model is doing. One thing to note as well, this is mentioned here. We also have a validation set, which is even different from the training and test set. So the test set, of course, you're not validating, you're actually getting the output of your model, the accuracy of it, and you're utilizing that to actually get accuracy as well. On top of that, validation set is data that it hasn't seen at all, right? It wasn't a subset of any of the input data. It could be new data that, yeah. So you usually, when you're setting up your experiments, what you'll do, let's say you have many different input files. Sometimes people will have a house price data set where it's a comma separated file. And they'll take this whole file to be a test set, or they'll actually have, you know, where they've created some fake data, or they have data that is represented that they downloaded from somewhere else. And they're also throw it at their model just to see how well it does. So in the code in 12 and 13, all it's doing is, these are the initial weights that is actually being put into the model to transform that input data to the output. So this is what it looks like in general, but it's just saying, okay, here was these initial weights, which is X train and X val and test. And then I'm gonna divide my
What is X val and test though?
These
Like,
are the
how is it represented in the data? Like, what is it?
So X val and test are actually they're actually what this pre-processing minimum min-max scaler comes up with. But all it is these are values that it's used to train and then actually test your model.
Okay, but where is it got, like, where is it picked from? Where do we get it from? I guess I'm just trying to see where it comes from. I understand what it's supposed to be doing, but how are we choosing it? Is it just set apart somewhere for that purpose?
Yes, it is just set apart somewhere for that purpose. So the X values come from here, but sklearn actually allows you to create that from the data that you've already given it. So
Okay.
it'll split your input data into however you want it to be split.
Okay, so could you go over line 12? So we have, I just want to see like the syntax and see what we're producing out of it. What's happening, you know, what the code is actually saying.
Okay, so it's saying we have X train, we have X val and test, and then we have Y train, then we have Y val and test. It's setting these values. So we have this function train test split, which takes in the X scale Y and test size equals 0.3. So the test size in this instance for that parameter, I think it's saying is taking 30% of the values that are in this house price data comma separated file. And usually what it does, it chooses those at random. And
Okay.
depending, some algorithms choose it at random. This Skylearn kit, from my understanding, it may choose it from the first or the last 30% of the actual data set, or the first 30%, but then other algorithms will choose them at random. So it'll take that and create a test set. And so all it is, this train test split is just splitting your input data into a training set, a test set, and then also an X val and test for Y and a Y val and test set.
So that function returns 4 things?
Yeah.
Okay.
And in Python, you can return many different parameters. What I can do is,
yeah.
I can look that up. 1 second. I'll move this out of the way. Can you see this screen?
Yes, we can see your screen.
Okay. Okay, so in this looks like it is the API that's available online for the Skylearn kit. But basically, this is just a library. It splits arrays or matrices into random train and test sets. So it was like I said, so it chooses your test set. It takes 30% of that test set and it chooses them at random. So in this example, you have the parameters that are passed into it, which is your arrays, the test set size, the training size. You can specify if you want it to be a random state. The default is none. And what that does is shuffles your input data into this split. And then you have a shuffle where the default is true, whether or not to shuffle the data for splitting. That actually, sometimes you can get a data set where somebody has already done some initial stuff to it, where it's been sorted or whatever. So sometimes you may want to shuffle it so that it's, you know, it's like playing cards or whatever. You want to shuffle it so that it's truly random as possible. And that shuffle parameter just says to do that before actually splitting the data into the training and test set. Stratify is default. If not none, the data is split in a stratified fashion using this as the class labels. So for our particular example, that doesn't actually apply. But here's a more simple example, but it returns a list containing the train and test split of input values.
Okay, I can probably
I can put this in the chat too
I
to
can look at it.
take a
So
look at the API.
okay. So going back to the code.
Yes. 1 second. Okay. Yes.
Okay, for number in line 13, the parameters of that train test split function, the X val and test and Y val and test, are they coming from the previous line?
Yes.
Okay. 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 I guess I'll just go through the documentation. Thank you.
You're welcome.
And Dr. Gloria, if you don't mind, if I may also add, so and I've worked a little bit with Malik, so I know I can visualize what he's trying to put across. So Malik, if you look on line 12, you see the line 12 in Python, you can have a left-hand side. Normally you have an equation x equal 2. In Python, you can have x comma y equal 2 comma 3. So x will take 2, y will take 3. So on line 13, what you see there, that train test split actually returns 4 sets of data.
Yeah.
First
I
set will
understand
be
that.
assigned, I'm sorry, first set will
Go
be
ahead, sorry.
Yeah, first set will be assigned to x val. X val is just a variable, and Dr. Gloria has given it x val for the evaluate the part of the data that will be used for the evaluation. That's what the x val is, which is a matrix. And then x test is a part of the data that will be used for the test, and that's also a matrix. The y is that labeled part, right? So the house price, is it above the median? Is it below the median? So that portion of the code chunk that relates to the y is going to be assigned to the y val. And then that portion of that house price data set, if you take the x block out, the y, which is indicating whether it's above median or below median, that will be assigned to the y test. So once you drop out of line 13, x val, x test, y val, y test will be populated. So then you can use it. You see, you can use it on the next line. All right. So it's sequential. If you run line 12 is going to give you the test and the train, and the val, and then you can basically you're splitting the data in 3 parts. If you look in the link I provided, you're splitting the data in 3 parts. But this train test only splits it in 2. split it 2 at a time. So what you do is you split it 2 at a time, you hold on to one, and you split the second one 2, and that gives you 3 data splits. Because you want to train, train, validate, and test. You want to split your data into 3 parts. So how would you do it if you have a splitter that can only split it 2 at a time? You split it 2 at a time, you hold on to one, and then take the one that can be split again. And so if you split the second one 2 at a time, then you end up with 3 data sets. And so that is what that block of code is doing. You want the training data set, you want the validation data set, and you want the test data set.
Yeah.
So this portion is doing that. Yeah.
Yep. Okay. Thank you both.
You're welcome. Thank you for that explanation. That was much better than what I gave, but basically everything that he said.
Dr. Gloria, there's one thing that I was experimenting with. So I see that you did the normalization to a min-max normalization, and if you do that, you indicated there that it helps the model perform better, which is true. If you don't normalize, I get an accuracy of 50%. So that's the line that does the min-max normalization. I think it's on line 10 of mine, where you, let's scale in.
Yeah.
Yeah, right, that portion, right. So if on line 10, or in the execution of 10, cell 10, if I assign that to an X, which is the one that hasn't been normalized, then once I go through the process, I only get 55% accuracy. But then with the normalizer, with that min-max scaling normalization to make sure the number falls between 0 and 1, or falls between the min and the max, it really improves the accuracy to your 82%, which is the one you just showed. And so is there a reason behind that? I mean, is it because of the way the algorithm is designed? Why the extra processing of normalizing? I think I can Google it, but yeah.
No, that's a wonderful question, and I should have covered that. Yes. So that is okay. So in cases where you have data that are on different scales, so let's say you had, in the case of my class, right? So there are some times where I have homework assignments that are worth 20 points, but I'll have tests that are worth 99 or 100 points, right? So sometimes you want everything to be along the same scale. So there is an assumption, and this is an assumption on my part that I should have went over, that when you have data that is along different scales, you want them to be on the same order of magnitude or have the same scale, because sometimes the larger numbers that are present, that would be present in the example of like exams, rather than homeworks, they would be overpowering to our actual model. So you want to convert those, and an easy way to convert things is normalization. Normalization, you can have it on a scale from 1 to 10. You can have it from 0 to 1. Whatever you say, you just have to be consistent. And in this example, it just converts all of the data regardless between this scale of 0 and 1, and it just allows us to not have overpowering numbers, especially if they're not on the same scale.
Thank you very much.
And something to note as well, usually this step is always included. So I should have mentioned that it's like an always included kind of thing, because we're coming from, different areas where even in biometrics, you can have pixel values that are on different scales as well for biometrics. You can have input data that also, just negative numbers in there as well. So if everything is converted, one doesn't overpower each other. And then in certain cases, you can also get rid of some of the errors that may occur in your data set, in your input data set. So a lot of times, being in computer science, you'll get data from someone else. And this step is important. It allows you to almost get rid of those values that are not a numbers or negative numbers, especially if it's not supposed to be a negative number, that could be outliers too.
And sorry, the TA is now becoming a student, but one last question, and then I'll students also. So when you go down for model 2, as part of the header, you indicated, or it's indicated that you're adding regularization. So I'm trying to figure out what, I mean, where or which option enforces, yeah, if you go down, yeah. So that's the first model. And then if you go down, you have the second model. There we go. So if you scroll up a little, there we go, yes. So if I compare this model to sequential layer with the model, the original model, the only thing I see here is that you're adding additional hidden layers. So I'm trying to figure out where does the regularization fit in here? I mean, or which part, if I'm describing this to a student, how would I say which line denotes the regularization?
You said the regularization?
Yes, please. So yeah,
yes,
there we go. Yes.
Sorry.
Yes.
Let's see.
Because I know regularization is if you're doing regression and you want to penalize that, you're using the lasso or the other type of penalization. But in here, I couldn't really make it out.
Yeah. Well, let me go back to the original model. Oh, so it has different, well, it has, like you mentioned, it also has more than it has way more hidden layers. And each hidden layer was a Relu function, and then it also had a sigmoid function at the end. It looks like the input shape of that was 10. Let's go back down.
And why do we have 32? Should that be 30?
No, I think it was 32 in the previous case.
It says 30 neurons somewhere in the non-code section, I think.
Batch size is different from neurons.
Oh, I see.
Yeah. That has more to do with like processing of the data to take it in batches.
Yeah, I think what Malik, that portion, I think Dr. Gloria, I think it may be a typo because I think you're describing what is below. You're describing line 20. So I think you said hidden layer 1 is 30 neurons with a Relu activation, and hidden layer 2 is 30. So I think maybe it's a typo on that portion, but the actual thing is 32. It should have been 32. Yeah, so if you go up to the first model, so if you go, where you are describing the model that, yeah, I think maybe a little type.
Oh, yeah.
Yeah, so let's go up a little.
See, here it's 32.
Yes, yes. So if you go up a little bit, bit, please. Yes. Think, yeah, more, a little bit. There we go. So, and there your description. So if you, scroll up a little bit, you are describing what is below. So what is below has 2 dense layers. One sequential with 32 hidden neurons, but then I think the text says 30 neurons. I think that's what Malik is referring to. So the text on top, it's a little out of it's two neurons less than what is actually being used.
Oh, yeah.
Yeah. So you say, yeah, our neural network has 3 layers. a hidden layer 1, a hidden layer 2, an output layer. So I think you are using 32, and we can see you using 32 consistently, but in the description it says 30. So
Yeah.
I think that's what Malik, Malik is okay.
No, yes, that's right.
I had a question about regularization. I'm not familiar with it. So why would we add regulation, and what is it?
So the reason, okay, not that I don't want to confuse you, but in this example, it was truly to show overfitting. And in this model 2, overfitting, remember, is you've trained your model too many times on the input data, and it's only representing that input data. Like it learned it too good. If you give it anything else, it's gonna perform or whatever. Not that I don't want to, I don't want to confuse you. So for purposes of like the way that you would possibly utilize this actual data or actual code, and
Come in.
okay. For purposes of how you would utilize this particular code, don't worry about that for now. I'll explain it more tomorrow.
I have a quick question.
Mm-hmm.
Okay, so you mentioned the different layers, the Relu, the Sigmoid, the other layers. Under what conditions would you use a particular layer?
You mean under what conditions would you
Use, for
utilize?
example, yes, a Relu layer, a Sigmoid.
Yeah. So Relu, remember, transforms the output to be 0 if it's negative, and then if it's positive, it just leaves it alone. Sigmoid transforms the output to be between 0 and 1. For the most part, and I can only show you in cases that we have utilized for biometrics, Relu activation functions have been utilized throughout, and then also 10H. But this is, when you're thinking of like deep learning, you kind of want to start out with Relu, and then you could, experiment with some other stuff. But start out with Relu as because it's almost like an industry standard now. It's as where you begin at, and if you know that your model isn't producing the best output, then you can start to look at some other ones. But you kind of always start out with Relu right now.
So do we see that it's a try and error process so you try Relu, it doesn't work, or you're not getting what you're looking for, then you try TAN, you try Sigmoid, is that what you're saying?
Yes.
Okay. Thank you.
You're welcome.
Yeah, so any other further questions for Dr. Washington? Yeah, so if there are no further questions, it's 1:30. So those of you who want to leave, you are free to do so. Dr. Washington will be with us again tomorrow to continue with this very informative presentation. William, I don't know if you have TA sessions or a bell TA session this afternoon.
Ebel, yeah, I think Ebel normally holds his TA sessions.
Yes, TA sessions at 4 to 5.
Okay, so TA sessions, as you heard, 4 to 5 p.m. Eastern Standard Time, and then also on Saturday and Sundays. So unless Dr. Washington will stay a few more minutes to answer any other questions, thank you all for coming and see you all tomorrow.
Sorry, John, do you want to mention the Tara information again?
Yes.
And also the survey, please.
Yeah, the survey is usually on the second day, so that will be tomorrow. So for those of you who came late, you have to create a Terra account for module 7. If you plan to attend module 7, you have to create a Terra account. The information is posted in Slack. It's also in the chat area here. So once you create the account, then you have to complete a very short form and send that to the module 7 team. The form will ask you for a Terra ID. So your Terra ID is just your email account login that you use to create the account. So again, the information is posted in Slack. It's also posted in the chat area here. If you look at the first few charts posted, I posted the information also there. Any other term? Okay, so
yeah, I'm sorry. The Terra ID, it's best to use a Gmail account. So if you don't have a Gmail account, please create one because the system works more with Gmail account than Yahoo or any other kind of email. So please try and create a Gmail account. That will be easier for you to create a Terra ID.
Okay, how about your institution email? Okay, I mean, Gmail, you can easily create it. So if you want to use that, just create one and then for that purpose. Okay, see you all tomorrow. Have a good rest of the day.
Thank you.
Thank you, Dr. Gloria. Thank you, everyone.
Thank you to the TA as well. Thank you.